Hello. Hello. Yeah, good afternoon, everyone. Yes, thanks for joining the class today under this very bad weather. Um, I hope everyone has went through a great spring break, and now we have to come back to school and do the remaining portion of the semester. Hope everyone will be doing well for the remaining a few weeks and finish this class with happiness. Okay, so first of all, our next quiz, the quiz in this week will be available after today's class. Again, there will be just the two single multiple choices questions, and you are given like 20 minutes. That should be more than sufficient. Don't just open that and don't do the problem, and never do the problem, then let the time goes by and exceed the limit. That will be that will unnecessarily hurt your grade. And another thing is I think the due for the homework 4 will be on next Tuesday. So we still have 1 week. So if you did not spend any time on homework 4, that's totally fine. We still believe you have sufficient time to finish that, but just take some time and plan for that. Then on next Tuesday, we'll release homework 5, and we probably will have 2 more, or at most 3 more homework assignments, or just written assignments, and that depends on our schedule. If the schedule is really tight, probably we'll have only 6 homework assignments in total. Okay, any question regarding our schedule? Okay, great. So let us first wrap up the joint distribution for discrete random variables. Then we will proceed to continuous random variables. I mean, their joint distribution. So if we have this is just a quick refreshment of what we have discussed in the week before the spring break. Right? So if we have 2 random variables, which are discrete random variables, meaning that they can only take discrete values, right? A finite number of discrete values. Or it's not necessarily a finite number, but it's just discrete values like 1, 2, 3, 4. You can imagine you can use some like integer or natural number to index every value the random variable can take, right? So the joint probability density function, right, which we call PDF, right, is defined as the probability of a special type of events associated with X and Y. So this joint probability are about the probability of the intersection of 2 events, right? The first event is X equals to A, and second event is Y equals B, right? So, sorry, if you want to write it in a more classical way, it should be written like X equals to A intersection with Y equals to B, right? What does this even mean? Or which set of samples are represented by this event? Did anyone recall? Yeah, this is event, right? This is a particular type of event associated with X, right? But what does this even mean? Any thought? Yeah, I'm just asking about this event, X equals to A. Yes, yes, right? Yeah, just keeping in mind, this is important for us to build a bridge between the real random events and the random variables. Remember, random variables are some kind of function. They map the samples outcomes from your real random experiments to some numbers. We talk about that. So this event, X equals to A, actually represents all the samples or all outcomes of your random experiments such that the evaluation of the random variable on this outcome equals to A. Right? That's the definition. Okay? So you see that we actually define this PDF based upon the probability on this special type of event. So one might ask, why do we just pick up this particular type of event? Actually, you can define many other type of events associated with A, associated with X. I can give you an example. For example, I can define an event like X belongs to some range, big A. So you can put big A to be, say, 1, 2, 3, right? I can define another event like this. So what does this even mean? In other words, what are the corresponding set of the outcomes represented by X belongs to A? Any thought? Yeah, we just need to adjust the definition here, right? So this guy actually is defined as the set of random experiment outcomes where the evaluation of the random variable at each outcome must belongs to this set capital A. That's it. Does it make sense? Right? So yeah, I mean, to have a better visualization, right? You can imagine this is your sample space, right? This is your sample space. And imagine you got a lot of like experimental outcomes, possible outcomes when you do random experiments. If you do it multiple times, you'll see different outcomes, right? So the sorry, the random variable essentially is just a mapping from the sample space from your real world random experiments to some real space. So this guy is a real space, right? This mapping is called random variable. So this event, the first event we mentioned, X equals to A. Basically means, okay, I pick up one point in the real space, which is A, right? I want to look at which set of samples through the X mapping will exactly be mapped to A, right? So the event actually is this set of samples, namely the green part. Does it make sense? Now, if we can extend this, right? We can extend this by choosing a set A in the real world space, in the real space, right? It's not only a single point A, it's a set A, right? It's a set big A, right? This capital A contains multiple real numbers. And then the corresponding event will be here, right? Will be the subset of samples such that, I'm going to use another color, such that the mapping from each sample while X will belong to the capital A. Then this whole set, the pink subset, represents the event. Any question? In other words, you can view it as a kind of like pre-image, right? Pre-image of this random variable X mapping. Is everyone okay with this? Because we're gonna talk about a very important things shortly. Okay. So our probability density function, PDF, however, is defined just based on the first type of event, namely the event represented as X equals to a single point A. And then if we look at the joint PDF, the joint PDF function of any given A and B is defined as the probability of the joint events. One event, X equals to A. The other event is Y equals to B. Then I look at, okay, what's the intersection of these two events? This probability is defined as the value of our joint PDF. Okay, this is our definition, right? So, and given this definition, we can fairly easy to compute the marginal PDF for a single random variable, right? How do we do that? How do we compute the marginal probability density function for X? Yes. Yeah, but then how do we compute that? You're telling correctly. I mean, in terms of concept, right? How do we compute that? Yeah, this will need us to sum over the joint PDF, right? So we just need to sum over the joint PDF for X and Y, but fix A, just sum over different choices of B. Those B are just all the values of the random variable Y can take. Any question? I remember for discrete random variable, for discrete joint distribution, we can represent it as a table, right? And where each cell represents, okay, at a particular value A and B, what's the density function value? And if you want to look at the marginal density for one variable, you just need to adds up all the row or adds up all the column, right? This is what we have practiced in the previous lecture. The fixed value of A, but you vary B. Yeah, that means like you're gonna sum over this way, or sum over this way. For example, right? Oops. For example, you got this one, right? You got this fxy. You know this, the row index A values and the column index B values. This might be 1, 2, 3. This might be 1, 2, 3, 4, right? You can represent this joint PDF by a table. And in each cell in this table, it is the value of the PDF at corresponding AB pair, right? Maybe this one is 0.01, this is 0.5, this one 0.1, this is 0.07, and so on, right? So if we want to compute, say, the marginal PDF for X only, that means you're gonna fix the A value and then sum over the joint density function values with all possible B values, right? So B could choose 1, 2, 3, 4. That means if you put A equals 1, then you're gonna sum over this row. Right? If you put A equals to 2, you're gonna sum over the second row, and so on. And similarly, if you want to compute the marginal density for Y, right, at any particular choice of B, right, you're gonna sum over, you're gonna fix B, right, but sum over the joint density at different A's. Any question? Okay, and if you look at this table as an example, right, if you want to look at, okay, what is the marginal PDF of Y at B equals to 4, how do we calculate? Yes, right? You just sum over this column, right? Yeah, yeah. We hope everyone is feels comfortable about this because, homework you'll follow upcoming homework you will definitely need to practice the calculation, marginal distributions, joint densities, and so on. Okay, so now we want to introduce what does it mean for independence. So we know if we have two events, by events we mean A and B are sets, right? Are two sets of the outcomes of the random experiment, right? So we see two events, A and B are independent if the following three conditions, any of the following three conditions are hold, right? So if you can show that the joint probability of the events A and B is equal to the product of their marginal probabilities respectively, respective marginal probabilities, or the conditional probability of A, conditional B, is marginal probability of A, or the conditional probability of B, conditional A, is just the marginal probability of B, then, I mean, all these three conditions are equivalent. Like any of this condition holds, it means like the events A and B are independent to each other. Now I want to extend this independence definition to random variables. This is a little bit different because random variable doesn't represent any sets. Random variable is just a mapping between the sample space and the real space, right? And how do we define these two mappings, X and Y, are independent? The definition is as follows. We claim two random variables, X and Y, are independent if and only if their joint density function value is the product of the marginal density function values for X and Y. And this equality must hold for every possible choices A and B. This is not a single equation. Actually, you have to make sure that if you enumerate every possible A-B pairs, this equality always holds. This is called independence. Right. So any question regarding the definition of the independence for the two random variables? Everyone feels comfortable? Okay, so then we want to look into this definition a little bit deeper, right? Not just memorize it. So we see that the independence definition for random variables are talking about the independence between two types of events. Between one types of events associated with the random variables, right? So this type of events are just like the random variable equals to some point, right? So remember, this guy is actually the joint probability that X equals to A and Y equals to B, right? This just represents the intersection of these two events, right? This probability must be equal to the probability that X equals to A and probability of Y equals to B, right? So see that if we define the event A as X equals to A and event B as Y equals to B, right? The independence between the random variables is only defined by the independence between these two events A and B, right? Big A and big B. Of course, you need to enumerate all possible such events because you can vary A and B, right? You can vary small a and small b. But the natural question arises, right? So is this sufficient? As we mentioned, although we define the PDF for a random variable, right? Only through the probability of this particular type of event associated with X. But you actually could define many different types of events associated with X, right? It's not just the X equals to some single value A. As we just discussed, right? For example, I can define another type of events like X belongs to, say, big A, right? This event is different from X equals to some single point, right? So a natural question would be, okay, if I define my independence of two random variables in this way, can we ensure for any other types of events associated with X and Y, are they also independent with each other? In other words, if I choose two sets, right? Big A belongs to R and big and does not belong to. Big A is a subset of R and big B is a subset of R. Then can we say if two random variables X and Y are independent, then we have these two events, x belongs to A and y belongs to B, are also independent. Can we conclude that? Can we? So even you enumerate every pairs of lines, they should be independent as well, right? Yeah, your intuition is exactly right, but we need a little bit rigorous a formal proof to show this. And also it can express the insight of the definition of random variable and why we define random variable just through this type of events is sufficient, because that type of events is fundamental. If we extend and the conclusion can arbitrarily extrapolate to arbitrary type of events associated with those random variables. This is a very smart definition. Okay, let's see this, right? So if you want to say whether these two events are independent with each other, we just need to check their joint probability, namely x belongs to A, intersection with y belongs to B, whether can be decomposed as the marginal probability of each event, okay? Does it make sense? Right? And then let's just do this, right? So according to the definition, right? So if you want to compute the probability, the joint probability of these two events, right? You just enumerate every pair of XY values and add them together, right? So that means you need to compute you're gonna enumerate every pair A and B, which belongs to the big A and big B respectively, right? And then adds up their probability. X takes A and Y takes small b together, right? This is just the total probability, right? You just you consider the sets of you consider probability for a set, and then you just add up the probability of every individual element in that set. Okay, and then this one, according to our definition, is just the joint probability density function, right? This is definition, right? And because we know that x, y are independent with each other, that means this joint density function can be further decomposed as the marginal density of x and marginal density of y. This is just to leverage our definition of the independence. Does it make sense? Right. So let's put everything together. So in the outer level, you're gonna do a double summation. That means you're gonna enumerate every element in the set capital A and every element in the set capital B, right? And then the summand will be just the product of the marginal density function for x at A and marginal density function for y at B. That sound okay for everyone? Yeah, let me know if you feel confused. Otherwise, I assume you feel this is like straightforward. Okay, so we can see that because this guy, right, this guy fxa is the marginal density about x, right? It has nothing to do with b. So that means this guy is constant with respect to b. So that means you can use the associative law, right? You can just move it outside. So that means like you can basically move the marginal density of x and a outside, multiply with the marginal density of y summing over all possible b's. It's just the associative law, right? So you see that now you have these two guys multiplied together, right? So remember, fxa by definition is the probability where x takes the value of a, right? So now you sum over the probability of x takes every element in capital A. What does it mean? What does it amount to? This is just the probability x belongs to A, belongs to capital A, right? Does it make sense? Right? Because big A is a set, right? So you want to look at what's the probability x belongs to A. You're gonna look at what's the probability x takes every single element in this capital A, right? That's what this summation do, right? And similarly, the second sum is the probability that y belongs to capital B, right? So you see that you got the joint probability of these two events can be decomposed as the product of the probability of two single events, right? So that means these two events, x belongs to A and y belongs to B, are independent to each other as well. Any question? Okay, and this is a good practice about the concept of joint probability density, and also it can extend your insight about this, right? So you see that although we define the PDF only based on event like x equals to some point, but this definition is powerful and comprehensive enough, and also very fit the intuition, right? If we say x and y, these two random variables are independent, that means any event associated with these two random variables are independent to each other as well. Okay. And this one we have previously practiced, right? So just have a quick review. Like this is the joint probability density function for SR, right? F SR, right? If I write it in better way, it would be SR and AB, right? It's a table. If I want to compute the marginal density of R, how should we do that? See, how do we compute the marginal density of S? Yes, exactly, right? So you see S could take 0 and 1, right? If I want to compute Fs at 0, you just need to add up all the density function values with S fixed as 0, but varying all possible R values, right? Which is just adding the first row, 5, 3, right? And similarly, if I want to compute Fs1, I just need to sum over the second row, right? Which is 0.47. Okay. Okay, the question is, how do we compute the marginal density function for R, say at 0? Yes, you just need to add along the first column, right? That means you just fix R to be 0 and add up the joint density function values across different choices of S. That would amount to adding all the elements in the first column, which is 0.45 plus 0.06, 0.51, right? Similarly, if you want to calculate the marginal density of R at 1, you just add up all the elements in the second column, which is 0.08 plus 0.41, 0.49. Right? And how do we decide whether R and S are independent or not? Any thought? Using that definition, right? Remember our definition, if R and S these are two random variables, right? If they're independent, we need to check their joint density value if is always equal to the product of the marginal density function values for both R and S, right? So that means you need to check at these 4 entries whether every entry can be represented as a product of the marginal probability, marginal density of R at A and marginal probability density function value at B. Right? Only when all the 4 entries have passed your test could we claim R and S are independent. Any question? Okay, so let us think about another, let us do another exercise. Suppose X and Y are 2 dice rolls. 2 dice rolls means that, okay, you just roll a dice independent for twice, right? So can we verify that these 2 events are independent to each other? The first event is that, okay, the first point, the point of the first row belongs to 1, 3, 4, and the point for the second row belongs to 1 and 2. How do we verify this? Any thought or any guess? Mm-hmm. 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 We take what? Mm-hmm. Okay, yeah, that's a good idea. So let me rephrase what you said, right? So one direct way of doing this is that, okay, I'm gonna construct the joint probability density function, right? So basically that means, okay, I'm gonna have a table, right? 6 by 6 table, right? Because you're gonna see at most 6 points, right? And you're gonna fill out this entry. And then from this joint density function, you can calculate the marginal density function, fx, and fy, right? And then you can, through the marginal density function, you can calculate the probability of the event x belongs to this range, and the probability y belongs to another range. You also throw this joint PDF to calculate what's the joint probability that x belongs to 1, 3, 4, and y belongs to 1, 2, right? And then you just need to check, okay, whether this guy is equal to the probability of this single event and the probability of the other single event. Right? That's one way of doing that. But here we want to use a more straightforward way, a more or even simpler way. So X, Y, 2 dice rolls, right? So that sorry. So the rolls are the dice are rolled like independently. So we will know that X, Y are independent, right? So as we mentioned, when X and Y are independent, then any event associated with X and any event associated with Y are independent as well, right? This is what we have just proved, right? Using some kind of definition and derivation to show that. So that means we can directly conclude this event associated with X and this event associated with Y are independent to each other as well. Yeah, yeah, you can use that. You can definitely cite the result we discussed in the class. But this just want to review some kind of like insight out of the definition of independence, right? But you can definitely follow the first way to calculate everything. That's also good practice. Okay? But don't forget our second insight. Sometimes it can bring you a much more straightforward conclusion. Any question? Okay, so let's take a rest for 5 minutes and then we can continue. Okay. So let's continue. Yeah. So we have talked about the joint probability density function for discrete random variables, right? Naturally, when we extend random variables to continuous, meaning that you might have like an infinite, uncountable possible values can take, right? And we would like to know how should we define the joint density function. So this part will be for continuous random variables. So like mirroring the case for the discrete, right? For discrete random variables, we usually define everything like PDF, independence, conditional independence, all the kind of stuff based on the event like x equals to some value. Say x equal to 3, x equals to 4, and this actually the PDF value for a discrete random variable. But we previously have discussed about that, right? You cannot use the probability of such event to define a random, a continuous random variable. Why? Because if x is continuous, you see that the probability of such event is simply 0. Right? And recall the example we discussed before, right? We want to look at the distribution. We want to look at the random events that how many the late arrival time in the class, right? So if we just count the time by hours, by minutes, you always have some probability for an event, the lead time is 5 minutes or 5 hours. However, if you can quantify the time like to be infinitely precise, meaning the time is continuous, then we see that with the rapid growth of the sample space, this probability becomes smaller and smaller, and at the end, or in the limit, it will go to 0. It will go to 0. So that means to deal with continuous random variables, we're not going to use this type of event anymore. Instead, we're going to define the event in this way. Namely, x belongs to a interval a and b. In English, it just means the event that x landed somewhere between a and b. Okay. And then, based on this event, we define the so-called PDF function, right? Probability density function for a continuous random variable. So our definition is a kind of indirectly because the PDF function doesn't reflect any meaning for some event. Instead, we say a PDF can calculate the probability of this type of event by doing integration. Right? The probability x landed between A and B can be calculated by integrating the PDF function f from A to B. And we have two additional constraints for PDF function. One is the PDF function must always be a non-negative. The second is if you integrate from minus infinity to infinity, that means you're going to integrate the PDF throughout the entire axis. Then what's the number? 1, right? So if you can find a function f that can calculate the probability for arbitrary A and B through integration, and this function f is non-negative, the integration from minus infinity to infinity is 1, then we call f a probability density function for this random variable x. That's the definition of the PDF for a single continuous random variable. Any question? Okay, great. So now, how do we extend this definition for multiple random variables? Okay. Let us just consider 2 random variables, x and y. Both x and y are continuous. So we will naturally consider the events x belongs to the interval a and b, and another event associated with y is y belongs to an interval c and d. Then we want to define the joint probability density function for x and y based upon the intersection of these 2 events. Right? One event is associated with x, the other event is associated with y. This is a natural extension, right? Because for a single variable, we define our PDF based on this event x belongs to the interval a and b, right? So now we want to extend it to 2 random variables. That means we're gonna be based on the events x for x and events for y, right? And both events take the form that, okay, the random variable are inside some interval. Right? Let us consider this event, right? The joint event x belongs to a and b, and simultaneously y belongs to c and d. So we define our joint probability density function f for random variable x and y in the following way. They are naturally extension for a single random variable, by the way. So first, we want the joint density is always non-negative. And second, we want the integration of this joint probability density function from minus infinity to infinity for both x, y will be a 1. Right? So, but right now, because we have 2 variables, right, in our joint density, that's why we need to do the double integration. We integrate not only along with x, but also along with y. And the third one, we require that for any such type of event, namely x belongs to a and b and y belongs to c and d, right? This probability can be calculated by the double integration of the joint density, integrating with x in the corresponding interval a and b, with y in the corresponding interval c and d. So that's the definition. Any question regarding this definition? Everyone's good with this? Everyone feels good about this? Okay, yeah. So that's good, right? So you can see that this particular type of event actually represents the XY pair should belong to some box, right? If you look at this one, this is a XY plane, right? So this even just tells that, okay, XY should be inside some box where X is belong A and B, Y belongs C and D. XY should be the inside in this box, right? And we require that you can arbitrarily choose this box where how large, how large is the height and the width, right? And the position, we require that the probability x and y are inside this box can be computed by you integrate the PDF function f over this box. Okay. Any question? This is a kind of like more intuitive um, explanation of this concept. Okay, so now I want to pay a little bit attention to this double integral, right? So what does double integration mean? It means that we have to compute the integration for twice, right? How do we compute double integration? So suppose I want to compute the probability x is between A and B, y is between C and D, right? According to the definition, this should be the double integration of the joint PDF function inside this box, right? So how do we compute this double integration? We just do two steps. The first step is to integrate x first. In this step, we're gonna fix y. Right? We treat y as constant and treat this joint PDF function as the only function for x. Then you do the integration along with x. Then the output will only depend on y, right? And next, you evaluate the outside integral. Because in the inside, you just integrate along with x, right? The result will be just a function of y. Then in outside, you just integrate this function of y along with y. Then you got the result. Any question? Okay, great. So someone asked, okay, why not I just first integrate with y and then integrate with x? It's totally doable. And I believe everyone has learned this before, right? So you switch the integration order, it doesn't change the result, right? You can first do the integration for y, right? In the internal level, so it will be fxy dy, and you fix x as some constant. So this result will be some function of x only. Then in outside, you further integrate this function of x along x. So those results are, the two results will be exactly the same. Any question? Okay, great. So now let us look at some example. So suppose this is my joint PDF for two random variables, x and y. So my joint PDF is defined as follows. When x between 0 and half pi, and y between 0 and 1, the density function value is 2y times the sine of x. In all other choices of x, y, the joint PDF value is simply 0. Okay. So you can imagine fxy, this is a pi over 2. This is 0 or 1, right? So the joint density function only is non-zero in this region. For all the other regions, they're just zero. The value is simply zero. Okay. So now we want to compute the joint probability that x is between 0 and fourth of pi, and y is between 0.5 and 1. How can we compute this? Use our definition, right? So we know that according to the definition of the joint PDF, the probability of x between an arbitrary interval A and B and y between another arbitrary interval C and D is computed by the double integral of x and y across A and B, across A and B and C and D on this with this joint density function and dx dy, right? And in this case, this is our A and B, right? A is 0 and B is pi over 4. And this is our C and D, right? C is 0.5 and D is 1. Then we just substitute those numbers for A, B, C, D and calculate the double integration, right? So let's do this, right? So the probability of this guy is a double integration of our joint density function. In the outer level is integration over x over y, which is 0.5 from 0.5 to 1, right? C and D. And in the inner level, we integrate along with x, right? The A and B is 0 and pi over 4 is here, right? So now we just need to calculate this double integration to get our probability. And to do this, we just need two steps. The first step is do the integration in the inner level, right? So in the inner level is the integration along with x, right? And to do that, we should treat y as fixed constant. Then this guy, if you feel the integration function 2y sine x, where y, if you consider as constant, right? So what is antiderivative of this guy? The antiderivative will be just minus 2y cosine x, right? You can double check with this, right? If you take the derivative of x, right, and the cosine x, take the derivative over x will be minus sine x, right? And then you got minus sign in front of it, and so the minus sign just disappear and multiply with 2y, you recover the function 2y sine x, right? So that means the inner integration result is just evaluate its antiderivative according to x, and at the upper integration, upper bound and lower bound, pi over 4 and 0, and calculate difference. Does it make sense? Right? So you just calculate, right? And this cosine x, when x takes pi over 4, it will give you square root 2 over 2. And cosine 0, what is cosine 0? It's just 1, right? It's just one, right? So that means after the inner integration, we have the result as a function of y, right? Which is minus 2y and times this constant, square root 2 over 2 minus 1, right? So the remaining step is just to further integrate with y, right? In this interval 0.5 and 1, right? So this one is constant, right? It's fixed. So the antiderivative for y is simply half y squared, right? And you multiply with 2, so the remaining term will just minus y squared and times this constant. Again, you can verify the correctness by taking the derivative over y. You're going to exactly recover the integration function. Right? Then the integration result is just to evaluate the antiderivative of y with respect to y at y is 1 and y is 0.5 and calculate difference, right? Which is pretty straightforward, which is this guy, right? If you use some calculator, it will be about 0.2197. Okay, any question regarding the computation example? Right? And if you lost about this double integration process, please open the old book about calculus 1 or calculus 2. Just do some practice and you will get familiar with that. There's nothing strange. It's just to do integration for 2 times. That's it. Okay. So similar to the discrete case, right? Given a joint probability density function for 2 random variable x and y, we can also calculate the marginal probability density function for x and for y. How can we do that? You just need to integrate the joint density function with another variable. Say, if we want to calculate the marginal density function for x, then you're going to integrate the joint density function with y only. And similarly, if you want to calculate the marginal density function for y, you're going to integrate the joint density function with x only. So that's how we get the marginal PDF for any single random variable. Any question? So you can see this is actually a natural extension of the discrete case, right? The discrete case, what you do is that, okay, you're gonna sum over all possible values your random variable y can take, right? And adds up the corresponding joint PDF function, right? But right now, because in the continuous case, y can take an infinite number of possible values, right? You cannot just add them up, right? You need to use the integration operation. And similar case for the marginal, you want to marginalize x. Any question? Okay, let's stop here today and see you on Thursday.